Here's what so far we talked about. We talked about the definition of electric field. We said that the electric field is defined by the force acted on test charge divided by the magnitude of the test charge, which is the positive. So the electric field is the direction of the force on the test charge. And then if you want to calculate the force on a charge in an electric field that we already know it's there, will be F equals to Q times E. And this Q can be used with this sign. If Q is positive, the force will be in the direction of E. If Q is negative, the force will be in the direction opposite to the electric field. So then we talked about the electric field of a point charge, which is KQ over R squared in the direction of R hat. Then we talked about electric field of a line segment. The electric field has two components, X and Y. X is along the line, Y is along the Y direction, perpendicular to that, passing through that point. So the X component is K lambda over R, cosine of theta of 2 minus theta 1. Theta 2 is the viewing angle of this end from the perpendicular point. And theta 1 is the viewing angle of the beginning of the line. This is very general. We can then apply to all different situations. And EY is K lambda over R sine theta 2 minus sine theta 1. In this case, say that this theta 1 and theta 2 are directional, starting from the perpendicular direction. Counterclockwise is positive, so theta 2 is positive, theta 1 is negative in this case. If the line extends from here, say, to here, then both theta 1 and theta 2 are positive. If the line extends from here to here, both theta 1 and theta 2 will be negative. So each one could be positive or negative. For example, here, electric field of a finite line of charge at a point on perpendicular bisector of the finite line. Means that this situation is symmetrical, so the two angles are the same. But this theta is positive, this one is negative, so theta 2 is equal to theta 1 equal to negative theta. And then if you plug in here, the X component becomes 0, the Y component becomes 2K lambda over R sine theta, sine of this angle. If lambda is positive, means the charge, positive charge is uniformly distributed over the line, the electric field is away from the line. If the charge is negative, the electric field will be toward the line. Sine theta can be written as opposite over adjacent in this right triangle. Opposite is L over 2 because the length of this is capital L, divide by L over 2 squared plus R squared, but you can reduce it to this form. So you can use this if you have the lengths, or you can just use that sine theta. This is easier to memorize. All right. If you let that go to infinity, means the line is infinite now. Sine theta becomes 1, so it becomes 2K lambda over R. This is the formula that you find in your book. This formula is not in your book. So this is for infinite line of charge with the uniform linear charge density over the line. And then this one is for field of a finite line of charge at perpendicular distance to one end. You see this, it starts from here, which is the origin, until X. And then you are at the distance R from one end, perpendicular to the line. Again, you see that theta 2 becomes theta 1 becomes 0. If you plug in here, you see these values. Then you can let X go to infinity, then you have semi-infinite line of charge. So for a semi-infinite line of charge at perpendicular distance R to one end, you have, again, two components. The line goes to infinity, theta becomes 90 degrees, and then cosine of 90 is 0, so this becomes just negative K lambda over R for X component, and sine of 90 is 1, so it becomes K lambda over R. So both of them have the same magnitude, but the X component is negative. That's why it's leaning toward the left. So this is interesting results that no matter how far you are from the end of this infinite line, the electric field makes an angle of 45 degrees to the line. Another geometry we considered was the ring. Uniform charge Q over this ring. It's a thin ring, means that the dimensions here are negligible. And then you are on the axis of the ring at distance Z from the center. Then the electric field at that point is away from the center if the ring is positively charged, is toward the center if the ring is negatively charged, and the magnitude is given by this formula, E equal to K cubed Z over R squared plus Z squared to the power 3/2. All right, we talked about the electric field of a disk of charge, a uniform charge density, surface charge density. This will be like that. Surface charge density is sigma. Electric field at any point on the axis will be sigma over 2 epsilon naught times 1 minus z divided by square root of z squared plus r squared. And for infinite plane of charge, you can keep z a finite value, but let r go to infinity. If you let r go to infinity, this fraction goes to 0, and what you're left with is sigma over 2 epsilon naught. So this is the electric field of an infinite plane of charge of uniform charge density sigma, surface charge density sigma. We talked about electric field of a circular arc of angle 2 theta naught at the center of curvature of the arc. Electric field is K Q over R squared times sine theta naught divided by theta naught. Pay attention to the fact that this theta naught is half of the whole arc, not the whole arc. This is where we left off. This is similar to one of the problems that we did before in chapter 21. There's a positive charge Q here, negative 3Q in here, and it says where on the axis is a point at which their net electric field is 0. Is it between the charges to their left or to their right? So there are two things to consider when you want to answer something like that. One is that at any point, which direction are the electric fields of individual charges and whether they can cancel each other or not. For example, in between, if you look at in between the two charges, look at this point, for example. Let me call this particle 1, call this particle 2. In between, particle 1 creates an electric field in here, and particle 2 also creates an electric field. Electric field of particle 1 at this point, is it away from the charge or toward the charge? Because the charge is positive, remember, we said that the electric field of that at any point is away from it. So this would be E1. And what about the electric field of particle 2 at this point? Is it to the right or to the left? Is it away from it or toward it? We can say at this point, E2 is this way because it is negative.
So that's different from attracting?
Yes, if you put a charge, if you put a positive charge there, it attracts it. But there's no charge there. It's just, it's just a point in space, and it creates an electric field at that point. Okay?
Thank you.
You're welcome. So you see that at any point in between, these two electric fields are in the same direction. So no matter what magnitude they are, they don't cancel each other. So there will always be some electric field at any point in between. So they cannot cancel each other in between. So this answer is wrong. Okay? So this answer is wrong because of that. Then let's go to the right. To the right here, E1 is away from 1. So E1 will be this way. And because it is away from 1, this is called E1. E2 means the electric field of this second particle will be toward it because it is negative. So it will be like this way, E2. But is it possible that E2 and E1 are the same magnitude and so that they can cancel each other? Remember, the electric field is KQ over R squared. So if you have a larger charge with the smaller distance, electric field is bigger. If you have a smaller charge, a larger distance, the electric field is smaller. Now you see in this situation, the -3, the larger charge, is closer. So E2 is always larger than E1. The smaller charge is farther away, so it creates a smaller electric field. So E1 is less than E2 at any point to the right, okay? Because one of them is always, no matter what distance you take, one of them is always larger than the other. There's no way they can cancel each other, even though they are in opposite direction. But if you look at this region, again, E1 is away from 1, so the E1 is this way, and E2 is toward, so E2 is this way. But because the smaller one is closer, at some distance can produce exact same electric field as the bigger one that's farther away. So at some point, these two become equal in magnitude, not everywhere, but at one point. This is the region where it is possible for them to cancel. So this is not also the correct answer. This is the correct answer. Okay? So you see, if the charges are opposite, in between, the electric fields are in the same direction. So that's out of the question. They cannot cancel each other. But if one of the charges is bigger than the other, and one is positive, one is negative, then it is usually to the side of the smaller one. Because if the smaller one is closer charge, it can create an electric field that is equal to the farther one, which is bigger. So that's how you determine the answer to this question. Part B says, is there a point of zero net electric field anywhere off the axis other than at an infinite distance? What do you think? In here, the positive Q creates an electric field in that direction, and -3Q creates an electric field at this point to this direction. And the positive Q is closer, right? And they can create, at some point, they can create the same magnitude of electric field. But can they cancel each other completely? Two vectors can only give you 0 if one is negative of the other. Means they have to be along the same line. If they're not along the same line, they cannot cancel each other. Right? If A plus B, two vectors in general, equal to 0 vector, B has to be equal to negative of A. That implies that these two vectors are along the same line. But here you see that if you are off axis, the two vectors cannot be along the same line. Therefore, they cannot cancel each other completely. It may result a small vector, but it cannot be 0. All right? Off axis. So the answer is no. Does it make sense? If sum of two vectors is 0, then one has to be negative of the other. That implies that they have to be along the same line. If they are not along the same line, one cannot be negative of the other. Therefore, the sum is never 0. That means that there's no point off the axis where the net electric field is 0. Okay? It says two identical circular non-conducting rings are centered on the same line with their planes perpendicular to the line. Each ring has charge that is uniformly distributed along its circumference. The rings each produce electric fields at points along the line. For 3 situations, the charges on rings A and B are respectively 1, Q naught and Q naught, 2, negative Q naught, negative Q naught, and 3, negative Q naught and positive Q naught. Rank the situations 1, 2, 3 according to the magnitude of the net electric field at A, point P1, midway between the rings, B, point P2, at the center of ring B, and C, point P3, the right of ring B, greatest first. Let's focus on part A at point P1. Which situation, 1, 2, 3, creates a bigger electric field at point P1?
I think it would be where the charges are opposite.
That's right. Very good. Yeah, you noticed that. And what about the other two?
They both cancel out.
Very good. Yes. All right. So this is the situations. This is all point 1. Situation 1, 2, 3. In 1, both of them are positive. In 2, both of them are negative. In situation 3, one of them is negative, one of them is positive. Okay? We said that the electric field of a ring of charge on its axis is away from the center if the charge is positive, if toward the center if the charge is negative. So let's call this ring number 1, call this ring number 2. And then because ring number 1 is positive, the electric field at P1 is away from its center. So the E1 will be this way. And because ring number 2 is positive, the electric field at P1 of ring 2 is away from its own center. So it means it's this way, this E2. And because they have the same charge, the same radius and everything, these two cancel each other. E equal to 0 at this point, because they exactly cancel each other. What about here? If both of them are negative, and this is 1, this is 2, the electric field of 1 is toward its center. So this time, this becomes E1. And electric field of ring 2 also is toward its center because it is negatively charged. So this is E2. Again, because of the situation is symmetrical, they cancel each other. So E becomes 0 here, the net electric field. But what happens in this situation, situation 3, the electric field of this 1 is negatively charged. The electric field of that one is toward its center. So this is E1. Electric field of 2 is away from its center. So it will be this way. So the electric field is, net electric field is twice E1 because they are the same. So twice E1 or twice E2. All right, so this is non-zero. So you see that 2 of them are 0, this one is non-zero. So the ranking is in situation 3, it is non-zero, so it's bigger than E in situation 2, which is equal to E in situation 1, which is 0. All right, the next one will be easier. What about part B?
Wouldn't they all have the same magnitude? Because the second ring is always gonna like be 0.
That's right. Yes.
At the center.
Very good. Yes. You know that the electric field for the ring is KQZ at the distance Z from the center. It's KQZ divided by R squared plus Z squared to the power 3/2. So if you put Z equal to 0 at Z equal to 0, we get E equal to 0, right? Because the denominator is non-zero, the numerator becomes 0. Right? So for point P2, the electric field of ring B is 0, no matter what charge it has. And the electric field of the other one has a non-zero value. In this case, it is in that direction. This is E1. In this case, it is in that direction, E1. In this case, it is also in this direction, E1. And they are all the same distance, the same radius, and the same charge magnitude. Therefore, the 3 magnitudes are the same. So we can say electric field of situation 1 is equal to electric field of situation 2 equal to electric field of situation 3, which is the same as E1. None of them is 0. They are the same magnitude. And then what about point 3?
Are S1 and S2 considered the same, but S3 would be weaker than S1 and S2?
That's very good. Why is that?
Because in S1, you have the magnitude of ring A and B pretty much equaling the magnitude of ring A and B in situation 2, either pulling or pushing the particle. But in situation 3, you have ring B pushing at the particle.
Yes.
Meanwhile, ring A is pulling at the particle. So
yes.
Yeah,
very good. Thank you. And of course, you're considering a charged particle there, but it doesn't have to be a charged particle there. We're talking about the electric field created at that point. So this creates an electric field E1, and the other one creates another electric field E2. One may be bigger than the other.
Professor, I have another question for you.
Yes, please.
Is it appropriate to view the electric field as a neutral particle, simply because the particle doesn't have any charge of its own? But for me, it's a little bit easier for me to visualize the particle.
Yeah, of course.
Rather than the field.
You can, but you can consider a particle there. But if we put a particle there, the electric field that's present at that point will apply a force on that particle. But you know that when you have a charge distribution, it creates an electric field everywhere. So it doesn't have to have a particle there. I understand it is easier for you to imagine that, but I want to invite you and encourage you to imagine the electric field around any charge distribution, regardless of whether a particle is there or not. Okay, so try to imagine, so at any point it creates an electric field, and then you can think of the electric field, which direction it should be according to the charge distribution. But to answer your question, yes, you can imagine a particle there, but you don't have to. All right? So in situation 2, both of these flip around. So the E of the ring 1 and E of the ring 2 are the same direction, but they both to the left, but still they add up. But in the situation 3, E1 will be toward the center of this A or 1. This is E1. And E2 is opposite of that. So here they partially cancel each other. In situation 1 and 2, they add to each other. In situation 3, they partially cancel each other. So the ranking would be electric field of the situation 1 is equal to electric field of situation 2, which is bigger than the electric field of situation 3. Does it make sense? Any questions? All right, so let's move on. Here it says a circular plastic rod in figure A with uniform charge plus Q produces an electric field of magnitude E at center of curvature at the origin of this coordinate system. In figure B and C and D, more circular rods, each with identical uniform charge plus Q, are added until circle is complete. A fifth arrangement, which would be labeled E, is like that in D, except the rod in the fourth quadrant has charge negative Q. Rank the 5 arrangements according to the magnitude of the electric field at the center of the curvature greatest first. So here we have only one. In part B, we have half a circle. In C, we have 3/4. Of course, we have 3 Qs in 3/4. In part D, we have 4 Qs. Part E has also a complete circle. And here we have positive Q, positive Q, positive Q, negative Q. So this is part E. Now, which one creates a larger electric field at the origin? What do you guys think?
I'm gonna say B.
B is the greatest.
Yes, because they're both positive, so we'll be either pushing it away,
All right.
or the electric field would be 2E heading down.
Uh-huh. All right. What about others? How do you compare others with each other?
Well, I feel like C, since it's at the bottom, now it's repelling it in the opposite direction, so you get about half E. And for A, it's only going to kind of move it to a different direction, but not as much as B.
Mm-hmm.
And then D would cancel everything out because it's at the center.
Okay, D, you get 0. And what about E? How do you compare E with those?
I don't know on that one.
Okay. Anybody else? I will talk about that soon. But
yeah, I'll go.
Yes, please.
I think E would be the strongest because the field is basically being pushed at a negative 45 degree.
Mm-hmm.
Right, that would be, it's being pushed from the positive Q rod in that way and pulled from the negative Q rod in that way.
Okay.
And then from there, I would say A, because you have, I would just say A. I don't really know how to explain it, but you have a kind of a no cancellation of forces because there's no opposing on either of the axes. And then I'd say B is going to be the third weakest, C is the fourth weakest, and D is the fifth weakest.
Okay, that's very good. You made some good points. Anybody else before I comment on that? All right. So you see, each one of these have identical charge, right? So each one of the quarters, they have identical charge. And remember that the electric field at the center of curvature is toward the center if the charge is negative, if away from the center if the charge is positive. So for example, for part A, we have an electric field this way. Let's call this EA. In B, each one of the two create the same electric field. On the first quadrant, create this, the same magnitude. In the second quadrant, creates this electric field with the same magnitude. So some of these two, you need to add them like vectors, becomes this vector, right? What about C? In part C, the first quadrant, this one creates vector like that, the same magnitude again. This one creates this, the second one. The third one creates that. How do they add up here?
Would A and C technically be considered equal?
That's right. You see that A and C are the same because these two cancel each other. What remains is one of the three.
Okay. And then in that event, would B still be weaker than A and C, or would it be stronger? Because
think about that. I'm going to comment soon. So in part D, as you predicted, you see all of them are in all different directions, and they all cancel each other. So this E is 0 in this case. And you notice that here E equals to E of part A. Somebody said part E is the strongest. Let's see what happens. First quadrant creates an electric field this way. Second quadrant creates electric field this way, away from its center. Third quadrant, this way. And the fourth quadrant, because the electric field of the fourth quadrant will be toward its center. So it creates another one this way. So here you see that E becomes twice EA, right? Because these two cancel each other, what remains is two vectors in the same direction. And each one is EA. So the net will be twice EA. Is that clear? And in part C, E equals EA. But what happens in part B? You have two vectors, each one is the same as EA, but they are perpendicular to each other. So they create a net that is the diameter of the square. Is the diameter bigger than the side? So here, net E will be, yes, it's square root of 2 times one side, right? If you have two vectors that are the same magnitude and they are at right angle to each other, you want to add them, you use either triangle method or parallelogram method. This is now showing parallelogram method. The parallelogram, in this case, happens to be a square. And the net will be the diameter of the square. Diameter of a square is always square root of 2 times one side, right? So in this case, it's square root of 2 times EA. In this case, is EA. In this case, is EA. In this case, is 0. In this case, you have 2 EA. Now the ranking is clear, isn't it? So E in part E is greatest because 2 is greater than square root of 2, greater than 1, right? The next one will be E in part B, which is square root of 2. The next one will be E in part A, which is the same as E in part C, which is greater than E in part D, which is 0. These questions are all reduced to adding vectors. In this, I drew all the vectors. This is part E, okay?